Okay, so this is the third part to section 7.1. And we're going to look at some word problems where we're going to find a resultant vector. And remember, a resultant vector comes from adding vectors. So we're going to be looking at some problems where we're finding a velocity or a resultant force. And we're going to want to determine, depending on what the question is asking, the magnitude of the vector and or the direction of the vector. Okay, so looking at this first example, a boat's speedometer reads 25 miles per hour, which is relative to the water, and sets a course due east, which is 90 degrees from due north. If the river is moving 10 miles per hour due north, what is the resultant or the actual velocity of the boat? Okay, so just to summarize this situation, the boat is driving and the driver is pressing on the gas. The speedometer reads 25 miles per hour and they're trying to drive in the east direction. Now, because they're driving the boat in a river where the water is moving 10 miles per hour due north, the boat is actually going to be traveling at a speed other than 25 miles per hour. Its speed is going to be affected by the velocity of the water, and its direction is not going to be east. It's going to be slightly off since the water is also moving in a different direction than east. Okay, so let's draw this picture in the two-dimensional plane, so in the XY plane. We're going to represent with vectors the velocity that the boat is attempting to drive at or move at, and then also the velocity of the water in order for us to find the resultant velocity of the boat, so the actual velocity of the boat. Okay, so in this plane, I'm going to label, this is north, west, south, and east. Okay, and the boat's speedometer, so the velocity that the boat is attempting to drive at has a magnitude or speed of 25 miles per hour and a direction of due east. So I'm going to draw a vector to represent that. So east direction, and then the speed being 25 miles per hour. So if the magnitude of that vector is 25 miles per hour, that means that this vector would terminate at the point 25, 0, right? Since this is 25 miles per hour. I'm going to represent the boat's velocity as a vector in component form, which would be 25, 0. Okay, if the river, I should have used blue for the river, but that's okay. So the river is moving 10 miles per hour due north. Okay, so let's say that that's the vector that represents the river. It would terminate at the point 0, 10. So I'm going to use R to represent the river's velocity. Oops. Put that into component form. So the actual velocity is going to be found of the boat. So the actual velocity of the boat or the resultant velocity of the boat, is going to come from adding vector b and vector r. So using those vectors in component form. Remember, if we're adding vectors in component form, we can just add each of the components together. So we would have 25 plus 0, 0 plus 10. So the vector in component form that would represent the resultant velocity would be 25, 10. And we could draw that in the picture here. Right, it would terminate at the point 25, 10. But just knowing the horizontal and the vertical components of the resultant vector doesn't really help us with describing the velocity of the boat, right? Like what does that mean that there's a horizontal component of 25 and a vertical component of 10? So why don't we find the magnitude and also the direction of this resultant vector? I'm going to give myself a little bit more space by adding a page. Okay, so to find the magnitude of vector v, we're going to take the square root of 25 squared plus 10 squared. That's going to equal to the square root of 725, which is approximately 26.926, and the units for the magnitude will be miles per hour. So the actual speed of the boat is going to be 26.926 approximately miles per hour. So the boat is actually traveling at a faster speed than its speedometer is reading because of the river moving, so the water moving. Let's find the direction that the boat is actually moving in, and we can see here that it's going to be different from east. So we're trying to find this angle right here. Since we're in quadrant 1, inverse tan of 10 over 25 is going to actually give us our direction angle. So if we pop that into our calculator, we get an angle of 21.801 degrees. And I'm going to say 21.801 degrees north of east. Right, since it's this angle here coming off of east in the north direction. So we'll say 21.801 degrees north of east. And then since this is a word problem, we want to summarize. So the actual velocity of the boat is 26.926 miles per hour, 21.801 degrees north of east. Okay, so let's look at our next example, another boat example, because the velocity of the boat is going to be affected by the velocity of the water. Okay, so a speedboat traveling 30 miles per hour has a compass heading of 100 degrees east of north. The current velocity has a magnitude of 15 miles per hour and its heading is 22 degrees east of north. Find the resultant or the actual velocity of the boat. Let's draw the picture again here. of the vectors that we're given information about. Vector quantities. North, south, west, east. Okay, so this speedboat is traveling 30 miles per hour. That's what the speedometer would read. And has a compass heading of 100 degrees east of north. Okay, so 100 degrees east of north would actually be down here. Okay, so the magnitude of this vector would be 30 miles per hour. This angle right here would be 100 degrees east of north. Well, we're going to want to represent this vector in component form. So this vector is going to have a magnitude of 30, but I need the angle, the direction angle in standard position here so that I can represent the horizontal and vertical components of this vector. Okay, so let's think about this. 100 degrees east of north, that angle right there would have to be 100 degrees, meaning this angle right here would be negative 10 degrees. So we could use the negative 10 degrees. I don't want to use the negative angle though. I want to use the positive angle. So the direction angle off the positive x-axis, right, this angle right here would be 350 degrees. Okay, not an angle on the unit circle, so we can't simplify that anymore. Okay, so the current's velocity, and current represents, it's not current like right now, it's current like the water. The water's velocity has a magnitude of 15 miles per hour and is heading 22 degrees east of north. Well, 22 degrees east of north, okay, with a magnitude of 15, let's say that that's the water's velocity. Okay, this angle right here, sorry, I didn't draw that very well. So this angle right here would be 22 degrees east of north. So I want to be able to represent this vector in component form as well. So I want the angle in standard position, right, for the direction angle. This angle I could find from doing 90 minus 22. Okay, so that angle that I'm going to use that's in standard position would be 68 degrees. So the horizontal component would be 15 times cosine of 68 degrees. And the vertical component is 15 times sine of 68 degrees. And we want to find the resultant velocity of the boat. Okay, so if we were thinking about adding these vectors using parallelogram method, right, since the tails are both at the origin, so constructing a parallelogram, we think the resultant vector would be this right there. Okay, so we're trying to find the horizontal and vertical component of that resultant vector, which would be the actual velocity of the boat. And then we want to find the magnitude and the direction angle of that vector in order to help us describe the actual velocity. Okay, so I'm going to call the water's velocity, the vector that represents the water's velocity, vector W, and I'm going to call the boat's vector vector B, and let's find vector V, which will represent the actual velocity of the boat. I'm going to give myself a little bit more space again. So vector V is going to be equal to vector W plus vector B. So vector V, adding the horizontal components, will be 15 cosine of 68 degrees plus 30 cosine of 350 degrees. And then the vertical component will be 15 sine of 68 degrees plus 30 sine of 350 degrees. Okay, please do not round, don't put these values into your calculator. We want, until we have our magnitude and our direction, we want to make sure that we have we're using exact values. You could store these the horizontal and vertical components into your calculator so that you don't have to type them out over and over again. Okay, so let's find the magnitude of vector V, which will represent this actual speed of the boat. So that will be the square root of the horizontal component squared. Instead of writing that out, I'm going to copy and paste. Plus the vertical component squared. And when we type that into our calculator, we get approximately 36.223 miles per hour. So that would be the actual speed of the boat. And now we want to find the direction angle. Now we're not positive, just because this is a sketch, we're not positive. We're pretty sure that direction angle, this angle theta, is in quadrant 1. But we can confirm that by finding theta. I'm going to call it theta star until I'm sure that I'm getting an angle in quadrant 1. You could also double check that the ratio B over A, so the vertical component over the horizontal component, is positive, and then you know that you'll get, when you take the inverse tan, you'll get an angle from quadrant 1. I'm just going to type inverse tan of, oh, I guess I could probably paste, huh? B over A into my calculator. And I get approximately 13.894 degrees, which is an angle from quadrant 1, meaning that is our angle theta, our direction angle. So we can use that. We can say the actual direction of the boat would be 13.894 degrees. How about north of east? Okay, so the actual, let's summarize with a sentence, the actual velocity of the speedboat is approximately 223 miles per hour, approximately 13.894 degrees north of east. Okay, let's look at this last example. I'm going to give myself an extra page on that one just because it doesn't look like there's very much room. Okay, so a barge runs aground outside the channel. So a barge is like this big flat thing that can carry things on water. So a barge runs aground, meaning the barge runs onto ground, it looks like onto a sandbar outside the channel. So a single tugboat cannot generate enough force to pull the barge off of the sandbar. So a second tugboat comes to assist. The following diagram illustrates the force vectors F1 and F2 from the tugboats. What is the resultant force vector of the two tugboats? Okay, so it looks like the first tugboat is pulling with a force of 15,000 pounds at an angle of 20 degrees from the other force. So we just need some sort of angle, something to describe the direction of the force. So 20 degrees off of the other force, which is pulling with 18,000 pounds. You can approach this problem in different ways. So if you just wanted to use the picture and the way that it is and draw your XY plane here, where your x-axis would cut that angle of 20 degrees in half, where then this angle is 10 degrees and this angle is negative 10 degrees, you can do that. My suggestion, just so that you're working in quadrant 1, and then when you take inverse tan of B over A, that you get the actual direction angle, would be to redraw this picture. Just in quadrant 1. So this is my x-axis and my y-axis. We're not given any information about north, south, east, west, so I'm not labeling those. So then F1 would be, let's say this vector, which has a magnitude of 15,000 pounds. And this angle right here would be 20 degrees. Okay, so F1, and they don't have the arrow drawn over. If you want to draw the arrow over the top of F1, you can. Could be written in component form as 15,000 cosine of 20 degrees when we draw our picture like this. And then the vertical component would be 15,000 times sine of 20 degrees. Okay. And then F2, I'll use green for F2. Okay, would terminate at the point, so I'm drawing F2 along the positive x-axis. Coming up with the horizontal and vertical components for F2 would be easy. It would be 18,000, comma 0. Okay, so we want to find the resultant force. I'm going to call the resultant force F3. So F3 is going to be F1 plus F2. Meaning the horizontal component would be 15,000 cosine of 20 degrees plus 18,000. And then the vertical component would be 15,000 sine of 20 degrees, and then plus 0. We don't need to write the plus 0. Okay, so we want to know the magnitude and the direction of our resultant force. So to find the magnitude of F3, we'll take the square root of our horizontal component squared plus our vertical component squared Okay, so when I type that into my calculator, and I'm typing the exact values in, I have not used my calculator until now. Oh, forgot the plus 18,000. Okay, so I get, after I type that into my calculator, I get approximately 32,502.831, and that's going to be pounds, right? That's the magnitude of the force, would be the weight. And then the direction angle, theta, since we're in quadrant 1, we can see if we were to use parallelogram method in order to draw the resultant force vector, our angle theta is going to end up being in quadrant 1. So inverse tan of, I'm just going to write it out, 15,000 sine of 20 degrees over 15,000 cosine of 20 degrees plus 18,000. Make sure you're in degrees if you're also typing this into your calculator. Okay, so I get approximately 9.082 degrees. And that would be, so in relation to what? Well, in our picture, we can see that that angle theta would be off of the angle off of the second force vector. So the way that we could say or describe this or summarize with our sentence is the resultant force is approximately 32,502.831 pounds and approximately 9.082 degrees off of the force that is pulling 18,000 pounds. Okay, or some description of that angle being off the second force vector. Okay, so here are a few examples where we